Perfect. Thank you, everyone. Thanks for organizing this. I really appreciate the chance to come to the first edition of this Lean workshop. I also appreciate that the scope of this workshop was deliberately broad and deliberately informal. I'm going to be presenting a bit of work here that's intended to be a contribution to MathLib. So although I'm thinking more in terms of software verification these days, and Lean is the perfect tool for that, Lean is also an awesome tool for stuff like this. So it allows me to both do my work stuff and have some fun on the weekends and the evenings with my math stuff. And that's basically what is going on here. So there's one of these 100 theorems that was presented earlier today, this list of 100 results that are being tracked for their formalization status. This is one of them that's not in Lean yet, and it's my goal to get this into Lean, although it'll probably take a number of steps to get there. And I'll show one of the crucial pieces that I have today. So probably most of the math people know this, but if you're not a math person, think about something like a tetrahedron or a cube or an octahedron or these other solids. There's a famous result that relates the numbers of vertices and edges and faces of these things. It's a constant, which is a kind of an amazing thing, first of all, to think of that. And then notice that we have a kind of alternating sum here. So there's the sign is switched here with when you go from dimension 0 to dimension 1, it goes to negative. This is an old result. This is from the 18th century by Leonard Euler, like almost everything. We're kind of like, just like in philosophy, say that everything is just a restudy of what Aristotle and Plato have already said, even today. We're kind of still like working with a lot of old results here. And in fact, this is one of the earliest results of algebraic topology, you would say. You might even say this kind of kicked off the field, so to speak, of algebraic topology. It's really an amazing thing. So there's a more general statement of this thing. Mathematicians love to move from 3 dimensions to n dimensions, right? And you see that there's a kind of alternating sum here where we take a kind of generalization of polyhedra in arbitrary finite dimensions. And then the result is a kind of, not necessarily a constant, but it's something that varies depending on the dimensions. So here's an amazing thing. Euler's polyhedron formula, as I presented it just on the previous slide, is about like these 3-dimensional polyhedra. But actually, in 2 dimensions, the same result actually contains the fact that a polygon has the same number of vertices as edges, which is actually, you need to think about that a little bit, but that pops out of this theorem. It's about the skeleton of a 3-dimensional, right? Yeah, so yeah. You have to be a bit careful with like exactly what D, right? I get that, yes, right. So I had done a formalization of this back as part of my doctoral dissertation. I was working in a system called Mizar back in the day, which still exists. It's still around. It's one of the like small players we talked earlier today about. Some of the big players like Isabelle and Lean is becoming bigger and bigger. But there are also small players in this field, and Mizar is one of them. I really like Mizar because it may be funny to admit this in a functional programming context, but my background is in classical mathematics. When I was working on these kinds of things, I really did not like functional programming. The idea that I would have to specify everything constructively was kind of I just want to do set theory. We're going to do mathematics is about set theory and classical logic, period. I don't want to hear any pushback about that. That was very close-minded of me. And I hope that for those of you who are younger going through your dissertation, I hope you grow up and kind of broaden your horizons, become less narrow-minded than me, more closed-minded. Anyway, so I actually had a bit of a kind of bad attitude when I initially approached this formalization for MathLib. Because I was initially thinking, hey, you know what? I'm just gonna charge into this thing and get the result as quickly as possible. And so what I did is I worked on a combinatorial approach to polyhedron, where you kind of skip all the real numbers. So you don't think about Euclidean space anymore. That's all gone. We just talk about combinatorics. We talk about basically something like I have a set of vertices and a set of edges. These vertices are incident with these edges. These edges are incident with these faces. That's it. So it's just purely combinatorial. There's a boundary relation. So think about the face of a polygon, of a polyhedron. And you say, well, which edges are on it? Yeah, yeah. Very simple. This is all very simple combinatorics here. You need to be a bit careful about the definition of polyhedron. This is a kind of like scare slide, like to reassure you that, yes, I have thought about the conditions under which this is valid. You can't just take any structure and say, well, Euler's polyhedron formula is valid for all these structures. No, no, no. There have to be some kind of conditions there. There's a condition which is basically like we have a kind of boundary of a boundary is empty condition. There's a bit of a game that gets played where we kind of stipulate that there's a minus one-dimensional face, which is incident to all the vertices. It's a kind of bit of an artificial condition, but that's fine. You also stipulate that there's a kind of whole polyhedron, and all the faces are incident with the whole polyhedron, just to kind of wrap everything up in a nice package to make the math work out. Probably the main driver, the real key to Euler's polyhedron formula is a result called the Euler-Poincare theorem. So this is something that Euler definitely did not do, but later towards the end of the 19th century and early 20th century, this got formulated. So the idea essentially is that if we take the number of, say, vertices, edges, and faces, that's what the CKs are doing here. And then we actually can form a quotient here based on this condition that the boundary of the boundary is always 0. That gives us a kind of quotient structure. And actually, the result is relating these two numbers, which is actually kind of amazing. Because when we think about a polyhedron, we add up the number of vertices, edges, and faces, and so on. And we do the subtraction depending on the sign. It's kind of amazing that it turns out that the results are the same when you take these quotients. An amazing result. And I can tell you that, well, I'm getting ahead of myself. So I was really excited. I fired up Claude Code. I got Lugal going. I got Lean Search going. I'm fired up. I'm ready to go. So I get my first version ready to go. But again, I was trying to just race to the end. I was just trying to get some kind of formalization just to get started with MathLib and whatnot. But the problem is that, oops. So notice that there's a big red thing here. Let me just say what the main point is. So yes, I did manage to get some kind of proof to work out. But I realized that this probably wasn't acceptable based on reviewer feedback because it didn't connect up with real numbers at all. It was just purely combinatorial. This is always an interesting question. What do you mean by Euler's polyhedron formula? What do you mean by a polyhedron? Is it okay to just have a purely combinatorial notion of polyhedron? Well, maybe not. So I love this because I didn't connect up with any of the algebraic topology stuff, or very, very little. So there's already a tremendous toolbox sitting in front of me, and I just said, I'm just going to do my thing. I'm aware of that. I'm not quite sure how to use it, so I'm just going to put it over and just, do it my way. I tried to do things in a bit of a weird way. There's a notion of augmentation of a chain complex, which exists in MathLib. I didn't know about that for a while. But then I thought, okay, I'm just going to plug into MathLib in a kind of simple way. Yeah, that's also kind of not very dumb. So I was very excited, feeling bold, made the PR, posted on Zulip. Yay! I got some feedback kind of within like a couple hours of this thing, and then more feedback came in a couple of days later, and I realized that this is a new BPR. So I really love Lean. I've been watching Lean for some time now, but I haven't really participated in a math lib. I've just been like a reader. I just followed it and admired it like a piece of art or something like that. But when you try to do the art, then you need to follow the standards of the other artists who are working here, right? And I kind of didn't know that very well. And so hence I closed my own pull requests. um, and the main thing is that what I was working on was just purely combinatorial. What about real numbers or real polyhedra? Fair point. And this doesn't connect with larger discussions about things that they want to add to math libs, such as combinatorial maps, some kind of combinatorial structures there. There's the issues about the Jordan curve theorem, which is a bit tricky. And I just completely sidestepped all of those discussions. I just jumped in and said, look at me. Oh, and here's an amazing thing. My formalization was actually inconsistent. It took a few minutes to even realize what was being said in the reviewer feedback. How is it possible that my formalization is inconsistent? It works. Like, look at this awesome stuff. And then you say, like, on line 5, I've already kind of gone the wrong way. This is great feedback, by the way. So I did change this, was a kind of simple error. I think this shows something interesting about Lean, because just simply changing the simple inconsistency or the simple error didn't actually affect anything else. So Lean wasn't exploiting the fact that it was obviously inconsistent. So just to wrap up, the current status is ultimately to try to get to a proof of Euler's polyhedron formula in MATLib, but I now realize that there will probably be a few stages along the way. The current status is I do have a PR in review that gets this Euler Poincare formula. Let me back up here. That gets this into MATLib. Sorry? It is not closed. But we'll see. I mean, we talked earlier about how reviews can take a long time. My background is in academia. I know all about reviews that take at least 1 calendar year to happen. So I understand. Oops. And I'm currently doing enough convex geometry to be dangerous. So the idea is that we're trying to connect up with real numbers and at least a certain kind of polyhedron, like convex polyhedron. That's not all the polyhedra, I know that. But if we can prove a result for convex in convex geometry, that should also be reasonable. For those of you who know some of the algebraic topology, the task here is to develop convex geometry at least enough to the point where I can associate a chain complex to this thing and show that it satisfies the conditions. There are other generalizations, other parts of algebraic topology that need to be formalized or could be formalized in this setting. The thing is that Euler's polyhedron formula, it's so beautiful because it starts so small and so concrete. You know, I have like a tetrahedron in my hand. But it goes into this vast space, and there's a whole playground of mathematics going on there. And it all started with this little formula. So I'm working on combinatorial maps. But again, the main thing is to work on the convex geometry as well. And that's it. That's all I have. Thanks.